Okay, so my name is Jamshad. So I'm working as an export sales engineer for Middle East in Airedale International Air Conditioning. We are a UK-based HVAC manufacturers, mainly focusing in the Middle East for data center coolings with computer room air conditioners and the close control units. So the topic of the presentation, as you can see, is evolution of data centers. So first, I will just go through the agenda of the presentation. So we will first go through the eras of data center cooling. Then we will just have a quick look to the challenges in the Middle East and how a typical data center in the Middle East look like. Then going into technical, we will just see the optimization of air temperatures, chill water temperatures, and how it affects the efficiency of a computer room air conditioners. Then we'll look to the low PUEs through smart controls or intelligent controls. First of all, we'll have a quick look to the backdrop of global megatrends. So the megatrends, these are the things happening on a global level. First thing, most thing is climate change. All of us know about the problems about the climate change. Let's look about the opportunity actually. So as per records, 82% of the economic potential of energy efficiency in buildings and more than half in industry is said to be remain untapped. It's untouched. So we have an opportunity there. So the other mega trend is the water scarcity. Of course, we live in a blue planet. Earth is a blue planet, but only 1% of the water is usable, actually. So as a result of these changing climates and urbanization, many of the world's major cities are facing a day zero. That's a big issue with the water scarcity. Then comes the digitization. Do you guys know that the human internet only has a 3.2 billion people on it? About half of the world population, we could say. But the Internet of the Things is expected to have 30 billion devices and things connected by this year of 2020. And this itself is a conservative estimate. The next megatrend is like urbanization. More than half of world's population now live in urban areas, increasingly in high density cities. So the combination of this urbanization and the digitization will see a global energy use increase by 50% by the year 2050. So data centers mainly are taking up an increasing amount of the share and still under a microscope only. Cooling providers such as ourselves are being pushed more than ever to innovate, to come up with more efficient products, you know. So that's all about the mega trends. So going to the eras of the data center coolings, we have seen higher temperatures in the server rooms or data centers in line with the ASHA recommendation by the year of 2011. We have seen efficient air management by aisle containment by the year 2008. Going to the aisle containments, there are like open aisle architecture where there is a mixing of air, there is no any containment, the cold air is supplied and return air is to the open space. Then we have the hot aisle where the hot air, as you can see the orange color or the red color, you can see the hot air between the racks are contained and looking to the aisle containment air management against the temperatures which they are related. As you can see the open aisle, the first one, you can see the return air temperature is about 25-24 degrees Celsius, whereas the supply air always will be in a range of 12-13 degrees Celsius. While in the cold aisle,
Sorry,
we will.
If I get in between, we had an interruption in the sound.
You getting any interruption?
I had an interruption on my side, and I see that a lot of people asked as well. So I see now people also say that the sound is back. I hope that's the case. If you could perhaps start the slide again.
From which you need the previous one?
Yes. Okay. If you go from there, please.
Yeah, please. Okay, no problem. So I was talking about the aisle containment or air management. We have open aisle architecture where there is a mixing of air with the room temperature or room air, and we have the hot aisle where the hot air is contained. We have the cold aisle where the cold air is contained. These all are like the arrangement of the server racks back to back or front to front. Then we have the in-rack hot aisle, which are like server in-rack coolings. For the on-rack, it's like a backdoor cooling. I was telling about the temperatures in different aisle containment solutions, which is one is open aisle. We are using a return air temperature of a 24-25 degrees Celsius. These are the temperatures to the crack unit or the cooling unit. And supply air temperature of 12-13 degrees Celsius, whereas in a cold aisle, we'll be using a much more higher, like a 27 degrees Celsius and a 15-16 degrees Celsius. In a hot aisle containment, you can see we are even able to use a return air temperature of 36 degrees Celsius and a supply air of 20 degrees Celsius. And in rack, same, we are using a hot aisle system there, 36 and a 20 return air. And on rack, even we are using a 42 degrees Celsius return air and supply air of 27 degrees Celsius. Now going to the next era, this is proximity cooling. It's itself is a phrase that we have coined, but describes the different cooling methods depending on the rack densities. Basically, I will come to that. So methods of cooling have evolved along with server density of applications. So for a colocation or enterprise data center where the server density is like a 4 kilowatt per rack, we are using a room cooling or an open architecture or an open aisle. In edge computing, we are using a 10 kilowatt server density, where we are using in-row cooling, that's a rack cooling systems. So in high performance computing applications, we are using even higher 20 kilowatt server densities, where we use backdoor cooling or on-rack systems. In a blockchain or cryptocurrency mining applications, we even see a much bigger server density of 30 kilowatt, where we use the application of this direct chip cooling, the latest one. We have also seen a migration away from DX to the chill water system by the year of 2011. We have seen making advantage of the ambient condition and using a free cooling in the year 2010. We even see the adiabatics cooling by the year 2013, then water optimization. Now, challenges in the Middle East listing down. Of course, it's a high ambient. We are having the design temperature of 46, more than even up to 50 degrees Celsius. Low rainfall and water scarcity, energy efficiency as a key in Middle East areas, conservative temperature management. Now, how a typical data center in Middle East look like? It's mostly like 100 to 200 kilowatt facility. Mostly used are DX systems. Some uses a dual fluid system with a chill water as a primary and a DX as a secondary. Mostly the set point design temperatures are seen as 20 degree in Middle East areas, and we are using traditional open architecture with raised floor open aisle system in Middle East data centers and server rooms. Now, getting into more technical optimization of air temperatures, how we can optimize the air temperatures and increase the efficiency of a system. Now, what temperature should you operate data centers at? That's the main question. Which temperature did you want to design a data center cooling unit? So we have some guidelines given by ASHRAE, American Society of Heating, Refrigeration and Air Conditioning. They publish some guidelines for temperature and humidity operating ranges of IT equipment. That is in a document ASHRAE TC 9.9. So that says about the data center power equipment thermal guidelines and best practices. So the main point here is the ASHRAE guidelines covers the server inlet air temperatures. That is the temperature that entering the servers or this entering the racks, not the air conditioning temperatures, not the return air temperatures of the air conditioners. So we need to look at that. The temperature mentioned in this section are the server inlet temperatures. ASHRAE has introduced two ranges, that is one allowable range and a recommended range. Allowable range provides IT equipment manufacturers and data center designers with a simple way to define product specification limits. So gathering the information from IT equipment manufacturers and the designers, they have plotted an allowable range which ranges from a 5 to 45 degrees Celsius the IT equipments can endure. Now, ASHRAE is stressing that the data center operators should plan to keep IT equipment condition within the recommended range, which is from 18 to 27 degrees Celsius. So in the guideline ASHRAE releases, so they are telling the server inlet temperature should be in a range of 18 to 27 degrees Celsius. Now we will look at different scenarios whereby increasing the air temperature can provide efficiency benefits to a typical data center. This is what ASHRAE recommended and allowable ranges look like when they are plotted on a psychrometric chart. So you can see the recommended envelope A1, A2, A3, A4 are the classification of IT equipments according to the temperature they can endure. Now, raising the air temperatures, as you know, the raising the air temperature reduces the energy consumption. Higher the return air temperature, higher the capacity, or in other words, higher the return air temperature, we can select the lower models of the crack units. So the graph's about to show energy consumption at air on temperature ranging from 20 to 36 degrees Celsius. So this is a ambient temperature plotted in hours which are measured in Dubai actually. At a set point of 20 degrees Celsius, you can see the energy consumption as in the green. While we increase the set point to 24 degrees Celsius, the energy consumption reduces. To 28 degrees Celsius, it further reduces. And at a set point of 36 degrees Celsius, it further reduces. The set points given 20, 24, 28, 20, 36 are the set points of the crack unit. Now we have plotted the energy consumption in units in these four air on temperatures. That is at 20 degrees, that is 553 unit, and 24, that is 517, 28, it's 494, and 36, 457. You can see the reduction in energy consumption while increasing the air on temperatures. We have taken DIVA tariff and we have just done an analysis on the cost per year. So these are the costs at 4 conditions, and you can see a difference of AED 36,000, which is equivalent to a $10,000 per year. We are having a saving while compared to a 20 degrees Celsius and a 36 degree air on temperatures. So let's see how these 4 conditions reflects on the ASHRAE recommended guidelines. So at a return temperature of a 20 degrees Celsius, you can see the air on temperature is like at 12 degrees Celsius, which is far below the recommended range of ASHRAE. This could result in overcooling. Dehumidification will also occur. At 24 degrees Celsius, it's still below the recommended range, still risk of overcooling, but the return air is well within the ASHRAE guidelines. At 28 degrees Celsius, air on and air off are comfortably within the allowable limits of A1 and very close to the recommended range of ASHRAE. At 36 degrees Celsius, supply air is well within the ASHRAE recommended, but this may fall outside the compressor operation envelope. So that's the conclusion with the DX system. As the DX systems are a return air control, meaning supply air temperature can be unstable, particularly at part load where we're using multiple or tandem compressors. Increasing air temperature can save energy, keep facilities within ASHRAE recommended limits, and also avoid overcooling of the servers. At higher air temperatures, air management in the form of ducting or aisle containment will definitely improve efficiency. So we would recommend transition towards a 28-degree return air in a typical data center based in this region, where we now see a 20-degree set point. We strongly recommend a transition towards a 28-degree. As a cost estimate, for a 200 kilowatt facility example, this would result in an annual energy cost saving of approximate 22,080, which is equivalent to $6,000. Now coming to the chill water system, all you know that chill water system has its own merits and demerits. The pros are like no refrigerant in the building, supply air temperature control, free cooling is possible, longer pipelines are possible, closer control with modulation of the flow. And the cons are extra capital equipment. Of course, chillers and pumps are required for a chill water system, and a larger pipework is required. Lower cooling efficiency, that's due to the additional cooling medium and a further heat transfer. So more complex to maintain or operate. So we ran an energy program in 3 different scenarios to see if a chill water system offered any benefits over the DX system, which we discussed before. For this, we have taken 2 different chill water temperatures, one is 612 and one 2026. For a 200 kilowatt facility, we have plotted the energy consumption with 2 different chill water temperatures. The orange color you can see is 612 degrees Celsius, and 2026 is the green color. So you can see saving in energy consumption while we are using a higher chill water temperatures. For a 500 kilowatt facility, the energy consumption is much lower. 1000 kilowatt, the higher temperatures, the energy consumption is much lower. While we are calculating on the cost, it's like for a 200 kilowatt, we are seeing an approximate $16,000 saving. For a 500 kilowatt, it's approximate a 34,000 saving. For a 1000 kilowatt, it's like 107,000 saving. Now, while these temperatures are plotted against the ASHRAE guidelines, excuse me, at 612, you can see we have taken in 2 facilities, 50 kilowatt and 100 kilowatt. The air on temperatures are well below the recommended range, and we are seeing a risk of overcooling there. At 2026, for a 50 and 100 kilowatt, supply air temperatures are more aligned with the ASHRAE recommended limits, as you can see in the plots. At 2228, the supply air temperature are also aligned. Now let's see the evolution of the chill water temperatures by the years. In the year 1980s, we have seen a supply and return air temperature of 612. When it comes to 1990 to 2000, we have seen an using of 712 degrees Celsius of chill water temperatures. In the year 2010, we have seen 814, 2019, 2026, 2020, it could be 2430. Now coming to the intelligent cooling. Of course, the key to achieving energy saving and impressive PUE or power usage effectiveness metrics is through use of intelligent control system. The CRAC units are equipped with intelligent controls. So whenever the equipment controls and the environment has an harmonized, we can optimize, we can have a higher efficiency system. So the combination of unit controls with the building controls or a BMS system can ensure HVAC systems run effectively at the most efficient operating settings. Supply, one of the possible cases, supply air stabilization in a DX system. As I told you, the DX systems are running on a return air basis, but with an efficient building management system, it is possible to monitor conditions at rack level. So we can have additional sensors at racks and monitor the temperatures at the rack level. This will allow the return air set point in the crack unit to be dynamically adjusted so that the rack temperatures to have a desired temperature. Now on the chill water optimization, maintaining a chill water wall set point at 90% open by dynamic chill water set point. So when say we have a stable system load, say the chill water wall is open 40%, so we can have the chill water wall open at 90% and use a higher chill water temperatures and at the chillers and increase the efficiency there. And by pump modulation, chiller sequences, we can attain chill water optimization. So that's all about the presentations, and the key takeaways from these are the continued digitization of our everyday lives is increasing. Of course, the demand for cloud and edge computing. As the data center industry grows, so too does its demand on the planet's natural resources, including power and water, is also increasing. As cooling systems and techniques evolve, there is an opportunity for data center operators in this region to conserve resources and save money by designing high efficient system, by utilizing high temperatures in the air side, by changing into high chill water temperatures or for the chillers, so developing to high efficient cooling solutions. Thank you. That's all about my presentation. So thank you. Up to you, Marcus.
Thanks, Jamshad.